AP Physics Dynamics Week 9 in the Simpkins Physics Corner. Today, ladies and gentlemen, I want to show you two examples of what we call equilibrium or static equilibrium and how our force equations and components can help us solve these, and then we're going to look at two acceleration ones as well. So let's get into it. We got a ball tied to a string. The first thing we always want to do whenever we're dealing with a problem with forces is draw a free body diagram, or our FBD. So we got FG down. We're going to have FT over this way, and we're going to have some holding force, just something tied to the wall or something like that. It says just before the ball is released and allowing it to swing back and forth, this is the situation we have. How large is the force that's holding the ball in the position, and what is the tension in the string? All right, so we've seen problems on inclined planes where the axis is kind of shifted. And here we're going to have a similar type of deal. If I can switch to my highlighter, you'll notice that the convenient axis to pick is this axis and this axis. Now, you may say, why is that, Mr. Simpkins? Well, if you look at the FT, we know the angle going on there. And so with that angle, we can go ahead and solve for the components of FT in order to make the components of FT fit to our axis that we just chose there, right? Now, the tricky part here is, of course, there's going to be an FTY, some upward contribution from the tension force, and there's going to be some FTX over here. Now, this is where you have to know your trig a little bit, because if you look, this angle is 30, which means this angle right here is 60, right? And so if you look at the position of FT and FY, if this is our hypotenuse, then this is our adjacent. And so in this case, AH of SOHCAHTOA takes us to use the cosine function. And in fact, if we were going to use this angle 60, we would say that FTY, let's go ahead and write this, FTY equals FT times cosine of 60. Now, I could have done sine of 30. In fact, that would get you the same answer. But I'm just going to go ahead and write that down. But let's go ahead and focus on what forces are actually balanced. Don't get confused because the FT is drawn here. In fact, I'm just going to go ahead and erase this now. And the reason why is I don't want anybody to think that the force of tension is acting and the components are also acting. We want to be careful to only pick one or the other. And what we notice here is, since we're at rest, two things have to be true. The first thing that has to move myself over here. The first thing that has to be true is in the y direction. In the y direction, FTY must be equal to FG. All right, that's not a big stretch. Look up and down. The other thing we know that has to be true is that FTX must be equal to our unknown applied force. Right? And so let's go ahead and flesh this out a little bit. If we're going to use 60 degrees, then I'll say like this, FT cosine of 60 degrees equals m times g. That's in the up and down direction. And then in the other direction, we're going to say that FT sine of 60, all right? Again, if, well, that's a little bit of a longer trig argument, but you see how this FTX would correspond to this side of the triangle, which would be the relative to the 60-degree angle that we've chosen here. That would be the opposite of the 60-degree angle. That's why we're using sine for x in this case, and that would be equal to f. All right, now we notice something here is that we don't know a lot of things, but what we do know is that ft is in both of these expressions. So check this out. If I solve this for ft, and make a substitution, that might get me somewhere a little bit closer. Now, the beautiful thing that you always want to remember is that sine of theta divided by cosine of theta is equal to tangent of theta. That's just a trig identity. And so if you can remember that, you can pick the algebra approach correctly. So in anticipation of that, I'm going to solve over here. I'm going to say ft equals mg divided by cosine of 60. All right, basically I just divided both sides by cosine of 60 in order to solve for that. Now watch what happens. I'm going to take this whole expression, ft equals that, right? Well, look, there's an ft over here. And this is called using a system of equations to solve. So this is what this is going to look like. It's going to look like mg over cosine of theta. Notice that's what just got plugged in for ft. And then there's still that sine of theta equals f. Okay, now we're getting somewhere, because sine of theta over cosine of theta is just tangent of theta. And so here we get mg tangent of 60 degrees. Sorry, I switched from theta to 60, but you guys see why they're the same. Equals f, and the cool thing is, now I can solve for the force, because I know what the mass is, it's 2. I know what the g is, it's 9.8. and I'm going to do tan of 60. Make sure you're in degree mode. Our force then would be 33.95 newtons. So that's the first part there, is how large is the force that's holding the ball in the position. Well, the cool thing is here, whenever you do a system of equations, at the end, if it asks you to solve for something else, you just have to circle back to your original expressions, and usually you can just plug your answer into one of your two original equations that you had to solve for it in the first place. What does that mean? I'm just cleaning up some space over here. Let's go ahead and drop this in. I'm going to take this guy, and you can pick either one. Let's pick this one. Let's say that FT equals mg over... No, I don't want that one. I can't pick that one. Because, look, you got to pick one. This, we know F here. We got to pick an equation that has the F in it and also has the FT in it, because we want to use the force that we just found to find the unknown force of tension. All right? And so what that's going to look like then, if I clean it up one more time, is I'm going to have to bring this over here, and we're going to rewrite this as FT sine of 60 is equal to F. And then I want to solve for the tension force. So FT, if I isolate that, it's going to be F divided by sine of 60. And so this is just a little algebra here for 33.95 divided by sine of 60, which would be skip 1,000 years ahead, which would be 33.95 over sine of 60. That's looking like, boy, this really went AWOL. This is looking like 39.2 newtons. All right, and so just to double check that, if this overall tension is 39.2, then it makes sense that this horizontal force only needs to be 33.95. Why? Because that horizontal force is only opposing some of that force of tension. All right, so the big idea is here where we took a force that was in a weird direction, just like we do on inclined planes. We took the components of that force carefully, all right, and then we derived two expressions. We said, all right, what forces are going on in the vertical direction, and what forces are going on in the horizontal direction? And we derived two expressions for those two things. Because it was in equilibrium, we knew we could set those forces equal to each other. Let's look at another one. We have a sign suspended from a horizontal strut of negligible weight. Oh, good thing that has no weight. We'll get to that later with rotational motion. I'll draw an FBD to show the forces and find the tension. All right, so here we go. Here is our first force that we have to worry about, is FG on this guy. But then, of course, there's also going to be an FT like this. Okay. Now, it says find the tension in the diagonal cable supporting the strut. Well, if you notice this, looking at this diagram, right now we have the idea that FT y would have to equal FG, right? Because the upward component, this component of FT would have to be equal to the downward force. But does anybody notice FT is to the left? What force is to the right? Well, the answer is the wall. Okay, so the wall is actually pushing there. But we might not have to get into that much detail yet for this one, because this just says find the tension in the diagonal cable supporting the strut. So here it is. Let's see what we can learn here. The y component of the force is this one. That would be opposite the 30 degrees. So in this case, we do use y sine. And the FT sine of 30 is going to be equal to mg. Now, it says a 200 Newton sine, and we know that weight is the force of gravity, so that's actually that side of the equation. And so here we just have FT sine of 30, okay? And then FT then would be equal to 200 newtons divided by the sine of 30, which if we drop that into our calculator would be 400. Now, this problem could get a lot more nasty if it said, like, what's the normal force pushing on the strut, but it doesn't, so we'll move on to the next one. This one is a bit of a beast. Let's see if we can get it done in 5 minutes. So, poor Beatrice, her wheels fell off her suitcase. Now she is forced to drag it across the floor. All right. We are given the mass of the suitcase, and we're given the pulling force. This is going to be 65 newtons here. What is the magnitude of the normal force acting on the suitcase due to the floor? Now, this is where things get a little tricky. All right. This is the first time we've seen where we have a suitcase like, we got our suitcase on the ground. And normally when you're on a flat surface, we can say that FG and Fn are equal to one another. However, think about this. If Beatrice is pulling up and to the right, now we have something a little funky going on, right? Now, the upward force of her tension, or we should say FTY, there's an upward component of her force pulling up. that's going to come into play too. So if we take the net vertical force, if we write the sigma Fy equals ma expression, right, which there's no upward acceleration, so we can just say basically we're taking up all the forces here. The normal force plus the, I'll call it Fty minus Fg equals ma. And in this case, we have Fn plus Fty equals, really it's 0 over there, there's no acceleration, so equal to Fg. And so this is a little tricky because it says, what is the magnitude of the normal force? So the normal force would be equal to mg, that's the Fg, minus Ft sine of theta. All right, now fortunately, I think we know all this stuff, right? Let's see if we do. We know 36 kilograms, we know 9.8. By the way, you should write the units in here, but I don't have time to do that, so I'm just going to fly here. This would be 65 newtons. Maybe I will write it there. And then sine of 40 degrees. So what we just did there, ladies and gentlemen, this is really important. Don't miss this today, all right? Anytime you have somebody pulling up and to the side, or let's say you're mowing the lawn, right? Let's say you're mowing the lawn and you're pushing down like this, right? You push on the handle down and forward, okay? Now you're going to have a scenario where your applied force and the force of gravity components are equal to the normal force, right? So you have to be real careful whenever you're pushing down into something or you're pulling up and dragging something. You need to take into account the vertical component of your applied force. And we do that here. So let's do a little Simpkins magic and make the numbers appear. 311 newtons, if we plug that in. That is the answer for what is the normal force applied from the floor. Let's continue. If the coefficient of kinetic friction between the suitcase and the marble floor is mu equals 0.13, find the frictional force acting on the suitcase. So a nice little review from last week. The friction force. Now, since we're moving, we have maxed out friction, so I'm not going to do that funky less than or equal to thing. I'm just going to say physics is fun. F-U-N. It's fun. Look how fun physics is. It's great. And so we're going to do the force of friction equals mu 0.13 times the normal force, 311. And let's get a little magic going here. 311 times 0.13 is just going to be our, bam, 40.43 newtons. Part C, what's the acceleration of the suitcase while she pulls with a 65 Newton force? All right, so we have acceleration. That implies unbalanced forces. And so what we know is that whatever her Ftx is, or whatever her horizontal component of her applied force is, it must be larger than the force of friction. We know that because if there's acceleration, then the forces are unbalanced. This is something we can say for sure. So let's come on over here and write sigma Fx equals ma and go from there. In the horizontal direction, we have her Ftx, her tension force that she's pulling with in the x component, minus the force of friction, and that equals ma. So the question says, what's the acceleration? So let's go ahead and plug all this in. Ftx would be, let's see, we got 65 newtons times cosine of 40 minus our ff we just solved for over here. So that minus 40.43 equals ma. I'm going to kind of chop that so it doesn't run into the next problem over there. And 65 cosine of 40 is going to be 49.79 minus 40.43 equals, and we also know the m, don't we? We know the m is 36 times a. So a little algebra magic here. All right, sorry about the jump there. I had a little PowerPoint issue jumping back into here. So that happens when I try to be fancy. All right, 49.79 minus 40.43 divided by 36. Our acceleration here, if I get my draw tool going, is going to be 0.26 meters per second squared is going to be our acceleration. All right. Then the next one is just a kinematic problem. Starting from rest, how long of a time must she pull with this force until she reaches a comfortable walking speed of 0.5 meters per second. So then we have like V initial equals 0. We have VF equals 0.5 meters per second. And then we would just use our acceleration equation. So VF equals V initial plus AT. And you could go ahead and figure out the rest of the math. And that would get you to something like 1.92 seconds. All right, so I had one more for you guys. I might put a little ancillary video on here, just another forces problem. But for today, what I want you guys to be familiar with is what happens when the forces are all balanced. You can set things equal to each other and flex with some trig. And then what happens when you are either pushing into a surface or pulling up. Be careful about your vertical forces.